Okay, we're looking at concavity today, which is the curvature of the graph. So if you look at the yellow graph here, this bit, can we see that if you look at how the graph is curving, this is concave up. It's sort of facing up, right? If you draw tangent lines on a concave up graph, they're always below the graph. So if you're drawing a tangent line, it's there, or it's there. Go away. Or there. But as soon as you get to a part that's, concave down, so the graph is facing down, the tangent lines would be drawn above the graph. All right? Does that make sense? Can you kind of see that? But it could be up, but not touching the part of the graph. You can't draw a tangent line here on the underside because you would hit the graph at 2 points. Right? A tangent line only hits the graph at 1 point. Right? If I drew a tangent line here and I extend it, I'm going to hit the graph at 2 points. But if I extend the ones like here, I'll never hit the graph again, right? And except where it's concave up. All right. So that's sort of a visual cue, but basically it's how the graph is facing. Is it facing down or is it facing up? Concave up is facing up, concave down is facing down. All right. So if we look at this graph here, f of x is equal to 1/3 x cubed minus x. And we sketch the derivative. Here's the derivative of it. Does everybody agree this is the derivative of that? X squared minus 1? Okay, there's the graph of that. If we take, and we know that, come on. If we then do the graph of the second derivative, i.e. we're going to do the derivative of this. What's the derivative of x squared minus 1? 2x. If I sketch that graph, what does that graph look like? Linear through the, what's the y-intercept? 0. Slope is 2. So it's a linear graph through the origin, right? And because it's mx plus b. If x is equal to 0, y is equal to 0. Yeah? Okay. Also, if we did what we did yesterday, and we took the slope of this part of the graph, that's negative slope, right? So it would be below the graph. The min becomes the y-intercept, and then this is positive slope, so it's above. That's the other way you can do it. Okay. Where is, on this graph, this section has a second derivative that is negative. Does everybody agree with that? Because it's below the x-axis. And this part of the graph, the second derivative is positive. Yeah? Okay. If we compare that, see, I want to see if I can get these on one page. Sort of. There we go. If you compare the second derivative and the values of those second derivatives, positive or negative, it's negative on this part, all the way to 0. Look at the graph, the original graph. What is the concavity on the original graph, f of x, in that domain? Down. Down. It's concave down. When the second derivative is positive, what's the concavity of the original graph? Up. So when the second derivative is positive, you have a concave up part of the graph. And when the second derivative is negative, it's concave down. Okay?
Does that apply
to everything?
No, if you have so can we tell if the second derivative graph where it's positive or negative by the concavity? You can tell the concavity by the
value of the second derivative.
Yeah, but does it work the other way?
Yeah.
Okay.
And the point where it changes, this point where it's 0, that's where the concavity changes on the original graph. And that's called a point of inflection. If you remember grade 10, we called it POI, and we had them hitting the x-axis. Remember those things? POIs can occur anywhere. They don't have to be on the x-axis. So we can say testing for concavity. If the second derivative, sorry? Yeah. So if the second derivative is bigger than 0, in other words, it's positive, then f of x is concave up. The second derivative is less than 0, negative. Concave down. And when the second derivative equals 0 / undefined, we're going to call those possible points of, oh my gosh. Of inflection. So when the second derivative equals 0, those are the possible points of inflection. If the second derivative is positive, it's concave up. If it's negative, it's concave down. And it's possible points of inflection is a lot to write, so we're going to call them PPOIs. You can write out the whole thing if you want to, but all right. All right, are we ready to practice? Okay. All right, can you do the first derivative for me, please? Of this function. First derivative, go. Please. This is good practice. Product and quotient rules are on the board. Do we have second derivative or first derivative? It's all right. 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 You just have to do first derivative, peoples. Just first. I'm going to give you the second. I just wanted to see if you can do the first. Yeah, I'll give you the second. All right. Well, if you want to keep going. There's the first derivative. Did everybody get that? Okay. Yeah. Yeah.
If I can x squared minus 4 plus negative half, and then the top one's half, and then you do half divided by negative half, like half plus half. If it's like 2 and 1, you factor on a negative 2 and 1, you do 1 plus 2. I think factoring out x squared minus 4 first part of negative 2. And then
Hang on.
what you have there is x squared minus 4.
Okay. Once you get to the second derivative, you have to figure out your possible points of inflection, i.e. where the second derivative equals 0 or is undefined. All right? So we say f double prime of x has to equal 0. Okay. When you're looking for it to be 0, you only have to look at the numerator. Okay? Will anything make this 0? No. Yeah. Because that's squared, right? If you put a negative number in there and square it, it becomes positive. and then you're adding a number to it. So a positive plus a positive is never going to be negative. Does that make sense to everybody? So nothing will make it 0. But the definition is what makes it 0 or undefined. So for undefined, you have to look at the denominator. What makes this undefined? Plus or minus 2. So we go undefined at x is equal to plus minus 2. Okay. These are your PPOIs, your possible points of inflection. Okay? And we do a little table or a little number line like we did with the critical points. Because at the end, the next step is to combine all this together. So we have -2 and +2. And we're testing the intervals. Okay? PPOIs, possible points of inflection. Now, you can pick any number on the interval from, well, -infinity all the way to -2. What number do you want to pick? -3. Okay.
Let's do 7.
You can do 7. Doesn't matter. You don't actually have to do a lot of math. What you need to do, I'll write out what we're going to do. So we're going to do, did you say 7? 7's not in that interval.
Well, it could be negative.
Okay. -7 or 3, it doesn't matter. I don't care. I don't need to see the math. Okay? So, look at, you're putting it into the second derivative. Now let's look at the second derivative. The top. Is the top ever going to be negative?
No.
This is important.
No.
It can never be negative, right? It doesn't matter what number I put in here. It will never be negative because that square makes it positive, right? So the top is always positive. Top will always be positive. It's the bottom that's going to determine everything. If I put -7 into here, what's -7 squared? 49 minus 4. Is that positive or negative? Positive number cubed is always, so positive over a positive is? So the second derivative is positive on that interval. If the second derivative is positive, are you concave up or are you concave down? Up. It's concave up. All right. The second interval is about as easy as it's going to get. What is the number that is screaming at you to put in? 0. Right? Zeros. I mean, you can pick any number you want from -2 to 2, but 0 makes it easy. We already know the top is always positive. If I put 0 into the denominator, 0 minus 4 is negative. Negative cubed is positive over negative is. If your second derivative is negative, you are concave down. They don't always alternate. Just want to put that out there. This one does, but they don't always alternate. All right. But if you pick like 3 squared is 9. 9 minus 4 is a positive number, so it's positive. So it's positive. Therefore, it's concave up. Is that all? I don't even remember what the question was asking for. What was the question? Determine the concavity. Okay. We know, so now we can say f of x is concave up from -infinity to -2 and 2 to infinity, and it's concave down from -2 to 2. Are we okay? I'm just going to give you 3 questions, and then that's going to be it for today. And you'll have no homework over the weekend. Page 192, 5, 7, and 11. You can see how these get a little more in depth when you have to do the second derivative. Okay? Because what we're going to do is we have to look at vertical asymptotes. We have to look at the second derivative test yet. But by mid next week, we're going to start putting this whole thing together to sketching a curve, a detailed sketch of a curve. You'll be doing what Desmos does in like microseconds. You'll take you like 25 minutes. But hey. All right, 192, page 5, or 5, 7, and 11, please. And that'll bring us up to Easter weekend.